Hello, welcome to this video. In this video, let us take one more problem on Otto cycle. Now, let us read the problem. An A standard Otto cycle. The moment I see the term Otto cycle, the first thing I do is I draw the PV diagram for an Otto cycle. I can also draw TS diagram of Otto cycle, right? So, let us have both PV as well as TS diagram for Otto cycle. So, PV and TS diagrams. So, we are pretty much sure about the process, alright. So, process 1 to 2 is compression, that is reversible adiabatic compression, process 1 to 2. Then 2 to 3 is constant volume heat addition, 2 to 3 is constant volume heat addition. Then 3 to 4 is reversible adiabatic expansion, and 4 to 1 is heat rejection in constant volume. So, these are volume constant, this is our reversible adiabatic or isentropic process, reversible adiabatic compression, this is volume constant, heat addition, QS, or heat supplied, we call it as heat supplied and heat rejected. Similarly, here it does look like this. Okay. So, 1 to 2 is reversible adiabatic compression, that is entropy constant. So, in a TS plot, entropy constant would look like this. Then we have volume constant heat addition and volume constant heat supplied here. Then 3 to 4 is reversible adiabatic expansion, and then 4 to 1 is constant volume again, and heat is rejected. See, the moment I see the term Otto cycle, this is what I do first. Now, has a volumetric compression ratio of 6. Volumetric compression ratio of 6 means the value of R is given as 6. R, you can say R is nothing but V1 by V2, and we also know V1 is equal to V4 and V2 is equal to V3 because constant volume there, alright. The lowest cycle pressure, where do we get the lowest cycle pressure? That is at 0.1. So, the lowest cycle pressure is 0.1 megapascal is given. So, megapascal means 10 power 6 Newton per meter square, and operates between temperature limits of 27 degrees Celsius and 1569. So, temperature limits means minimum and maximum temperature. So, T1 is 27 plus 273, that is 300 Kelvin, and similarly the highest temperature is 1569. So, plus 273. 1569 plus 273, that is 1842 Kelvin. So, 1842 Kelvin. Now, what has been asked? Calculate temperature and pressure after isentropic expansion. Now, ratio of specific heat, that is gamma, is given as 1.4. Now, we are interested in calculate temperature and pressure after expansion. That means we are talking about 0.4. So, after isentropic expansion means we are interested in calculating P4 and T4. So, what is temperature after expansion? Pressure after expansion, alright. Now, how do we do this? We have been given the value of R, that is compression ratio. Now, I think we will use the process 3 to 4, that is where we can get the values of this 3 and 4, right. So, process 3 to 4 we shall use, and in process 3 to 4 we know that P3 V3 power gamma, that is because PV power gamma is equal to constant in 3 to 4, right. So, P3 V3 power gamma is equal to P4 V4 power gamma, alright. Now you can say that we are interested in finding out P4. So, P4 is equal to P3 V3 by V4 whole power gamma. Now, P4 can be found out P3. Now, what is V3 by V4? Now, V3 by V4 is 1 by R, right? Because V4 by V3 is R. So, this is 1 by R whole power gamma. So, P3 is known to us P3 is not known. So, we will have to find out P3, then we should come back to this point. So, if we have known this value of P3, I think we should have got the values of P4. Now, how do we find out P3 is of next importance, right? So, let us come back now to this point after finding out P3. So, this cannot be solved. So, I will go for process 1 to 2, then 2 to 3, then I think we will be able to do this, all right. So, I will take, first we will start with process 1 to 2. Now, process 1 to 2 is what? P1 V1 power gamma is equal to P2 V2 power gamma. I can use this because process 1 to 2 is also PV power gamma is equal to constant. Now, P2 is equal to now we have P1 V1 by V2 whole power gamma. All right. Now, P2 is equal to, therefore, P2 is equal to P1 we know 0.1 into 10 power 6. And what is V1 by V2? V1 by V2 is R. Now, R power gamma. So, that is 0.1 into 10 power 6 into R is 6, power gamma is 1.4. So, that we can solve 0.1 into 10 power 6 into 6 power 1.4. So, that will be 1.22 into 10 power 6. So, 1.22 megapascal or 1.228. So, 1.23 will take 1.23 into 10 power 6 Newton per meter square is our P2. Okay. Now, once we have the value of P2, I think let us go for T2 also. So, let us go for T2 also. So, I will keep this to the later stage. So, this is what we should do first. Then we shall go for T2. Now, how do you find out the value of T2? The value of T2 can be found out by using the same process 1 to 2, but pressure and temperature are volume and temperature relationship, all right. So, I will use the same PV power gamma is equal to constant. So, let us say P1 V1 power gamma is equal to, this is to find T2, all right. This we use to find P2, okay. So, to find T2, we use the same trick, but let us go for temperature and volume relationship. So, temperature and volume relationship. So, we would like to eliminate using this trick PV is equal to MRT, we want to eliminate pressure. So, in place of pressure, I would say I will go for MRT by V. So, MR cancels out. So, I will not use MR here. So, in place of pressure, I will use T1 by V1 for gamma, because MR gets cancelled out both the sides, because MR is constant between 1 and 2, right. And I mean, for a closed system, wherever you take, the mass and this characteristic gas constant remains same. So, in place of P2, it is T2 by V2 power gamma. So, T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1, or you can say T2 is equal to T1 V1 by V2 whole power gamma minus 1. Now, T2 is equal to T1. Now, V1 is V1 by V2 is R for gamma minus 1. Now, T1 is known to us 300, R is 6, power 1.4 minus 1. So, that will be our T2. 300 into 6 power 0.4, 1.4 minus 1. So 614.3. So T2 is equal to 614.3 Kelvin. So that is how we can find out. That is how we can find out the value of T2. Now let us go for finding out P3 and T3. So that is possible. Let us use process 2 to 3. What is constant between process 2 to 3? So this is now, let us go for process 2 to 3 then. Process 2 to 3. Now what is constant between process 2 to 3? Volume is constant. So volume constant. What do we mean by volume constant? PV is equal to MRT. Let us use this trick. So for volume constant, we can say I will send this volume to the right side, temperature to the left side. So P by T is equal to MR by V. Now mass is constant already, R is constant and volume is also constant. We can write P by T is equal to constant. So whole right side is constant. Therefore, we can write for process 2 to 3 P by T is equal to constant. Now, what do we mean by P by T is equal to constant? P2 by T2 is equal to P3 by T3. All right. Now, I think we know P2, we know T2, we know T3. So, only unknown is P3. So, we can find out that. All right. So, P2 is 1.23. So, P2 is 1.23 into 10 power 6. P2 is 1.23 into 10 power 6 and T2 is 614.3 Kelvin and P3 is the unknown and T3 value we know, which has been given 1842 Kelvin. 1842 Kelvin. So, the only unknown is P3. Let us find out the value of P3. Okay. So, 1.23 into 10 power 6 divided by 614.3 alpha equals, now unknown is, let us say, alpha x divided by 1842. So, the only unknown is x. If solve for x is equal to 0, we'll have answer 3.688 into 10 power 6. 3.688 into 10 power 6. So, 3.68 megapascal we can say. Okay. Now, let us now go to process 3 to 4 and try to find out what is required. So, this is where we had come back because we did not know the value of P3, correct? So, now I think we have the value of P3. I think we should be able to find out P4 as well as T4. Now, P3 is 3.688 into 10 power 6 and the value of R is 1 by 6 whole power 1.4. Now, we have so 3.688 into 10 power 6, 1 by 6 whole power 1.4. So 300.194 into 10 power 3. 300.19 into 10 power 3 Newton per meter square. So, if you want to keep it in terms of 10 power 6, we can divide this by 10 power 6. So, I think we can get the like 0.3 into 10 power 6. So 0.3 into 10 power 6 Newton per meter square. If you want to just to have a comparison and try to write everything in megapascal so that we can have a clear comparison, all right. So 0.3 into 10 power 6 Newton per meter square. Now let us go to the last part. The last part is finding out temperature after expansion. Okay. Let us go for temperature after expansion. Same between process 3 and 4. Between process this process is to find T4. This was we had used to find P4. Okay. Now the same equation P3 V3 power gamma is equal to P4 V4 power gamma, and we know this equation. I don't want pressure, I want temperature. So in place of pressure, I will write MRT by V. MR gets cancelled out, so in place of pressure, it is simply T3 by V3, V3 power gamma, T4 by V4, V4 power gamma, and this goes to the top, V3 power gamma, and this will be -1 if it goes to the numerator, and if you add the powers, V3 power gamma -1. Similarly, T4, V4 power gamma -1, and then T3, V3 by V4 whole power gamma -1, T4. And therefore, T4 is equal to T3. Now, what is V3 by V4? Just check. V3 by V4 is 1 by R, alright, 1 by R, 1 by R whole power gamma -1. So, T3 is known to us 1842, 1842, 1 by R value is compression ratio 6 and this is 1.4 minus 1. So, that will give us the value of T4. So, 1842 into 1 by 6 whole power 0.4. So, that will be 899.55 Kelvin. So, T4 is equal to 899.55 Kelvin. All right. Thank you.